Welcome, students. So, we will resume our discussion. So, in the last class, we were discussing about the transmission fundamentals for wireless communication, and we stopped here at the spectrum of speech and music, and we were discussing how the actual transmission system limits the bandwidth of a signal. Ideally, the signal can have infinite bandwidth, but practically, when you are transmitting it through a system, through a transmitter and a channel, then the bandwidth of the signal needs to be limited to design an effective practical system. So moving on, in today's lecture, we will start with these data communication terms. So data means any entity that conveys some meaning or information, and signals are electric or electromagnetic representations of data. So so note that in the previous lecture, when we were defining a signal, we said that a signal is something that conveys an information, which is still true, but signal is the electromagnetic representation of the data which contains the information. So in indirectly, the signal also contains some information. So that's the whole point. And transmission means communication of the data by propagation and processing of signals. So you have some data, you are putting it on some signal, or you are mapping the information onto a signal, and then you are transmitting the signal through a propagation media. For wireless communication, it's the atmosphere or the air. For any other form of communication, for example optical communication, it will be an optical fiber and so on. So so the data again can be analog or digital, and examples of analog data is your video and audio, which are inherently analog in nature because they continuously vary with time, whereas digital data is more of a discrete sort of data where you have some discontinuities. So the example can be text or integers. So so moving on, the signals that actually carry the data can also be analog and digital. So analog signals are continuously varying electromagnetic waves that may be propagated over a variety of media. So the variety of media includes the air in case of wireless communication, optical fiber in case of optical communication, a copper cable in case of coaxial cable communication, and so on. And also the frequency is important. So depending on the frequency of the signal, we sometimes choose the appropriate propagation media. So so analog signals can propagate both analog and digital data. All right, so you have to be careful here to distinguish between an analog signal and then analog data. So signals can be analog and digital, data can be analog and digital, and then each of them can carry each other. So basically, an analog signal can propagate analog and digital data. Similarly, a digital signal can propagate analog and digital data as well. We will see. So digital signals, it's basically They are a sequence of voltage pulses that may be transmitted over any medium. Okay, um, so when you have a high voltage, you call it a level 1. When you have a low voltage, you call it level 0. You can define more than two levels, and then you can have some appropriate voltages uh, corresponding to that levels. And the main idea is that the digital signals have uniquely defined discrete and finite set of levels, and these are generally cheaper than analog signaling. Since you have a finite set of levels, it's much easier. The hardware is easy to design than, let's say, uh, in the case of an analog signal. Digital signals are also less susceptible to noise interference, but then they suffer more from attenuation. Okay, so so if you recall, I showed a diagram in your digital communication class where you have a digital signal like this, let's say, and then if you have noise on top of this, then let's say let's say let's say if you have noise on top of this, no, let's say this is noise on top of your data. Okay, so these are less susceptible to noise interference. This means that since it has unique levels, ones and zeros, and they are usually distinctively apart, so then the um, noise can affect these levels, but you can still distinguish between these levels. So for example, since they have a unique distinctive difference between these levels, the chances of noise being so high that your zero get wrongly interpreted as a 1, and 1 getting wrongly interpreted as a 0 is less. So we saw that in our introductory lectures in digital communication. Here also I will show you a diagram to be able to appreciate it further. And then digital signals suffer more from attenuation. Why? Because uh, from the same logic, so you have the distinct levels, let's say zeros and one, that is helping you to distinguish between a 1 and a 0 in the presence of noise because of this difference in the levels. But then if you have more attenuation, these levels actually fall down. So the levels, because of attenuation, will go down. Okay, and if the levels go down, then it's difficult to detect them in the presence of noise if the noise is very high. So digital signals can propagate, again, analog and digital data. So as analog signals can propagate both analog and digital data. So so as I said, so there are two types of signals, analog and digital, and then there are two types of data, analog and digital. So 2 cross 2 gives you four possible combinations. So we can have digital data over digital signal, we can have analog data over digital signal, and then we can have digital data over analog signal, and then analog data over analog signal. And depending on the combinations, each of them has some advantages and disadvantages, as mentioned briefly here. So um, let's see the four cases. So so let's say you have analog data, which is your voice, sound waves as you are speaking, and your telephone is converting that analog data into an analog signal. So you are propagating the analog signal that is carrying your analog voice data over the telephone channel. Then in case of your digital data uh, carried over an analog signal, you need to have a modem in between to convert, or rather to put the digital data over an analog signal. So the analog signal is usually modulated on a carrier frequency. So again, these details we will study gradually throughout this semester in digital communication, and also a little bit here in wireless communication. So what is a carrier frequency, what is modulation, and so on. And then if you want to transmit analog data over a digital signal, then you need a codec in between that will put your analog data over a digital signal. And then finally you can have a digital data that is transmitted with the digital signal, and for that case you need a digital transceiver to do this operation. So see, there are different devices that can map your different types of data over different types of signals. So when we talk about analog transmission, basically it transmits analog signals without regard to content, and the maximum distance that your signal can propagate is limited by the attenuation. So you can transmit the signal as long as the amplitude of the signal stays within a certain threshold. If it falls below that because of attenuation, then you have to use amplifiers to boost the signal's energy. And you can have cascaded amplifiers, so you can have multiple amplifiers cascaded together. Let's say this is an amplifier, then you can have another amplifier, and so on. So you have cascaded amplifiers to boost the signal along its path. Then digital transmission, this is basically concerned with the content of the signal, and attenuation endangers the integrity of the data. And you can what you can do is that when you have a digital signal to transmit your digital data, then you can use repeaters that recover the signal and retransmit, and you can achieve a greater distance of transmission. If your signal is analog, when you are transmitting digital data, you can do it both over digital signal and analog signal. So when your signal is analog and your data is digital, then you can do retransmission by having some retransmission devices that recovers the digital data from the analog signal and then generates a new clean signal and then transmits. So depending again on the combination, whether it's a digital data or an analog data, whether it's a analog signal or a digital signal, you have different types of transmission devices, and also you have different types of retransmission devices, let's say, to recover the signal if it gets degraded or attenuated. So you can have amplifiers, which is a retransmission device. You can have a repeater, and then you can have other forms of retransmission devices based on the exact scenario that you are using. So now comes the concept of channel capacity. So so in a wireless channel, let's say, or in any media, any channel, wireless or optical or any guided media, there are impairments in the channel. So for example, noise is one of them, attenuation is another one. You will see in wireless channels there are also multipath fading effects that we briefly discussed in the introductory class. So these effects actually uh, degrades the signal. Okay, so when you are transmitting a signal, ideally what you are sending you just get at the receiver if there are no noise or no impairments. But because of the impairments, the signal quality falls down, and there is a maximum rate at which you can transmit data over a given communication path, and that maximum rate is determined by how much noise is present and other impairments present in the channel. So the theoretically every channel has a channel capacity. So beyond that you cannot transmit. That is the maximum rate. So imagine you have a highway, and your cars are running in the highway, and you have a speed limit, let's say. Okay, so let's say 120 kilometers per hour. So this is the maximum channel capacity. Let's say if you imagine that your road is the channel and the car is the signal that you are transmitting, then every road has a speed limit. Okay, in kilometers per hour or miles per hour. Okay, so that is the maximum that you can safely attain. Similarly, for every channel, be it a wireless channel or a wired channel, you have a channel capacity, which is the maximum rate at which data can be transmitted over that channel or over that communication path. So this slide again highlights what's the effect of noise on a digital signal. So let's say you have this digital data in ones and zeros, and you are transmitting it over a digital signal. So whenever let's say you have a 1, you have this level. Whenever you have a 0, you have this level. So usually we have a high level when we have a 1 and a low level when we have a 0, but this example shows the opposite. Doesn't matter, as long as you have a definite rule of mapping the bits into the signal, that is okay. So here in this example you have low when it is 1 and 0 when it is high. Okay, so now imagine that you have a noise which is varying over time like this. So now if you add this noise to your signal, your signal will look like this. So this is the effect of impairments. Your original signal looks clean and crisp, but in this case the noise is degrading the signal, and it looks a little bit distorted in this case. So now if you are observing the signal, the noise plus the signal at different points of times, let's say your sampling times or the observation times are these, then you can see that most of the times you can detect the signal properly. So you have received a 1 and your original data was 1, you have received a 0, the original data was 0. So let's say the rule is whenever we have a high, we will interpret it as a 0. Okay, and whenever we have a low, we will interpret it as 1. That's the rule here. Okay, so it's the same rule when we are applying at every sampling time. Let's say at this time we have a low, so this is detected as 1 and original data was also 1. Let's say at this time we are detecting a high, so we are concluding that it is a 0 and the original was 0. So most of the times we are making correct decisions, but let's say here we have a error. Why? Because at this sampling time when we are observing here, it is basically high. Okay, so high means 0, so we are detecting a 0, but actual signal, if you look at the actual signal, this is low, so this was a 1. Okay, and because the noise is so high at this region, you are detecting this 1 as a 0. So this is an error you are making because of the noise. Similarly, here also the noise is so low that you are making a mistake here. Okay, when you are observing at this time interval and then you are making an error. Originally it was a 0 and you are observing it as 1. So as you saw that noise and also other impairments can degrade your signal and you can make mistakes. And then also you have this concept of channel capacity, where you can have a maximum possible data rate that you can attain when you are transmitting through a channel. And these two things are related, this concept of noise degrading your signal and the channel capacity. And because of the noise, imagine that the noise are the roughness of your road. So if you're traveling, if you are driving on a car through a road, and if it has a speed limit, let's say the speed limit is your maximum data rate that you can attain, and that speed limit is related to the roughness of the road. If the road is very bad and rough, then you cannot drive fast. You will have an accident if you drive very fast on a very rough and bad road. But if the road is smooth, which means like there is no noise, then you can attain a higher data rate or a higher channel capacity. So that is the relation between channel capacity and noise. So data rate is the maximum rate at which your data can be communicated. Bandwidth, the bandwidth of the transmitted signal is also important. So this is constrained by the transmitter and the nature of the transmission medium. Noise, as you saw, is the average level of noise over the communication path, and error rate is the rate at which errors occur. So because of the noise and also your data rate, let's say your noise is high and you are still trying to send your signal at a higher data rate, then you will make lot of errors. Okay, so just like if your road is very rough and you try to drive very fast, then you will feel bumpy, and there might be damage to your car. So that's how these things are related. So moving on, when we are talking about channel capacity, so basically the channel capacity is related to the bandwidth of the signal, as you just saw in the previous slide. So bandwidth is important. So you can imagine bandwidth as the breadth of the road. So let's say this is your road, okay, and you are driving your car. Okay, so the car is basically your signal, let's say, and the width of the road is basically the bandwidth. Okay, and how bad is the road, the roughness of the road. So let's say you have many holes in the road, or the road is generally rough and broken. So these are basically your noise. Okay, and then the maximum speed limit, let's say the road has 100 km/h speed limit. Okay, so this is your This is your channel capacity. Okay, so this is the maximum speed at which you can drive. Okay, so the data rate or the speed of the car is governed by this channel capacity or the speed limit. Okay, so with these analogies in mind, your channel capacity can be defined in terms of bandwidth and many other things. So the first definition comes from Nyquist. So Nyquist defined the channel capacity C equals to twice of B, where B is your bandwidth. So when you have two voltage levels or binary signaling, zeros and ones, then you have C equal to twice of B. When you have multi-level signaling and M is the number of discrete signal levels, then you have C equals to this stuff, where a log of M to the base 2 is added. Okay, so we will be able to appreciate this a little more when we will study multi-level modulation and signaling in digital communication. But right now, just appreciate that for binary signals, we have C, the channel capacity, defined as twice the bandwidth. And for multi-level signaling, we have an added factor of log M to the base 2, where M is the number of discrete signal levels. So now there are other definitions of channel capacities as well. So there is, apart from the Nyquist channel capacity, there is the Shannon's channel capacity. But before going to the Shannon's channel capacity formula, we have to see what is signal to noise ratio. So this is basically the ratio of the power in a signal to the power contained in the noise. Okay, as simple as that. So typically this is measured at the receiver and it is given as a log ratio. Okay, so it is defined in decibels. So SNR in dB is basically the 10 log to the base 10 of the actual ratio of the signal power and noise power. So you can define SNR as a ratio like this, or in terms of dB by taking the log and then multiplying with 10. So a high SNR means a high quality signal, because your signal is very strong compared to the noise. So so SNR sets the upper bound on achievable data rate. So again, this is very intuitive, as you saw in my road and car analogy. If your signal is strong, if your car is very strong, let's say it has a very strong engine, okay, then even with slight difficulties in the road, the road is a little rough, even then you can drive your car at a certain speed. Okay, so SNR sets the upper bound on the achievable data rate. So how strong is your signal compared to the noise, or how strong is your car compared to the roughness of the road, you can achieve a certain upper bound on the speed or the data rate. So with that in mind, Shannon defined channel capacity by this formula, which says C, which is your channel capacity, is your bandwidth times log to the base 2 of 1 plus SNR. So here you can see that your SNR, how it drives the channel capacity. So you have two formulas of channel capacity now. One is defined purely from the signaling levels perspective, and the other one is from the SNR perspectives. So this is the theoretical maximum that you can achieve for your channel capacity C. Okay, but in practice much lower rates are achieved because of other impairments. Here in this formula we are assuming that the noise is white noise, and then other noises like impulse noise etc are not accounted for. Then there would be attenuation and delay, distortion, and many other things. So this is a very simplified formula assuming that noise is white noise, and therefore this gives you the maximum upper bound of achievable channel capacity. If you factor in the other impairments, then you will have a much lower channel capacity than this theoretical maximum limit given by Shannon's formula. So again, in digital communication class we will try to derive this formula at some point in this semester. So you will see then how this formula evolves from some basic assumptions. All right. So let's do an example. An example to check the Nyquist and Shannon formulations. So let's say you have the spectrum of a channel that is between 3 megahertz and 4 megahertz, and your SNR in dB is given as 24 dB. So your bandwidth is 4 minus 3 1 megahertz. You have to convert your SNR, if it is given in dB, to the ratio. So in pure ratio terms, your SNR is 251. And now you can use Shannon's formula to calculate the channel capacity. So your bandwidth is 1 megahertz, so 1 into 10 to the power 6 times log to the base 2 of 1 plus the SNR. And if you compute this, then this will be roughly 8 megabits per second. So this is the maximum achievable data rate that you can have with this SNR and this bandwidth of the channel. Now, if I ask you how many signaling levels are required to achieve this particular channel capacity, so you can calculate that from the Nyquist formula. You can plug in C equal to twice of B log M to the base 2, and then you have everything here. You know C, which is 8 megabits per second. You know the bandwidth. So you can calculate your M easily as 16. So you need 16 signaling levels to achieve this particular channel capacity with this particular SNR and bandwidth. So now I would ask you to solve a problem which is similar to the previous one, just to get your ideas right and strengthen your understanding. So let's say a digital signaling system is required to operate at 9600 bits per second. Now, if a signal element encodes a 4-bit word, what is the minimum required bandwidth of the channel? And then repeat part A for the case of 8-bit words. Okay, so I will give you some time. You can pause this video for a while and try solving this problem from the concepts that you learned before, and then I will give you the solution. All right, so here is the solution. So you can use Nyquist equation first. C equal to twice B log M to the base 2, and then you plug in the value of C, which is given. So 9600 bits per second is your channel capacity here. So to achieve that channel capacity, what are the number of or what is the minimum bandwidth required? You are given that you have a 4-bit word, so your number of signaling levels is 4. Okay, so therefore you have 9600 and then twice of B and log 2M is 4. Okay, So you have a 4-bit word. So 2b times 4, and then you calculate your b to be your 600 hertz. Okay, so this is the ignore these numbers. This is basically the steps. Okay, that is confusing. Okay, so log 2m is 4. Okay, because you have a 4-bit word, and your capacity is 9600 bits per second. So simple use of the Nyquist equation will give you the bandwidth to be 600 words. And if you repeat the part A for the case of 8-bit words, then it will be 9600 equals to twice b times 8. Oh, sorry. So this is for the 8-bit word, 600 hertz, and for 4-bit you have 1200 hertz. So that's the final solution. So moving on with the transmission fundamentals. So your transmission media can also be classified into different categories. So basically, the transmission media is the physical path between the transmitter and the receiver, and the physical path can be guided as well as unguided. So in case of guided, basically the electromagnetic waves are guided through a solid medium. So that medium can be a copper coaxial cable, can be an optical fiber, can be a twisted pair copper cable, and so on. And in case of unguided media, basically you have the outer space. In case of your satellite communication, the atmosphere. In case of other forms of wireless communication, and when you have an unguided media, we usually call it as a wireless transmission. And at both the transmitter and the receiver, we have antennas to transmit and receive the signals. And those antennas again can be directional and omnidirectional. So we will get into the details of these later when we will study the details about the wireless mobile communication and cellular communication. So moving on again, the electromagnetic spectrum that is used for telecommunications. So you are basically sending electromagnetic waves, and you can have different frequencies of those electromagnetic waves depending on the medium that you are using. Okay, so if you are using, let's say, a twisted pair, then you can send from frequencies of hundreds of hertz to 10 to the power 8 hertz. Okay, so that's the range. Okay, then if you are using, let's say, AM radio, then you have to play with a very small range of frequencies between 1000 between 10 to the power 5 to 10 to the power 7 hertz. And then for optical fiber, let's say, you can work with terahertz frequencies. Okay, 10 to the power 14 to 10 to the power 15. So there are different types of communication, different types of media of communication, and based on that you can support different types of frequencies and different types of wavelengths. So if you look from the frequency perspective, then you have them in hertz, and then you can have extra low frequency, then you have very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, and so on. And if you look from the perspective of the wavelength, then you will have, let's say, microwaves, millimeter waves, centimeter waves, and so on. Okay. So general frequency ranges for microwave is 1 gigahertz to 40 gigahertz. For radio frequency, you have 30 megahertz to 1 gigahertz. For infrared, roughly the frequency range is between 3 into 10 to the power 11 to 2 into 10 to the power 14 hertz, and so on. Then for terrestrial microwave, you have a special type of microwave antenna to use, in the shape of a parabolic dish, and then it has certain applications in long haul telecommunication, short point to point links between buildings. You can have satellite microwave. So again, these are different types of applications of wireless communications based on the media that you are using or the frequencies of the electromagnetic wave you are using, and so on. You can have broadcast radio. So there you see that there are different frequencies to play with and different types of media are used. So the last concept that we will do in this lecture is the concept of multiplexing. So as you recall, the concept of channel capacity. So usually the capacity of a transmission medium is very high compared to the capacity of a signal. Okay, so if you go back to the analogy of the road versus car, usually the road is very big and it has more capacity. Let's say it can have multiple lanes in the road if it is a highway, and you can drive many cars on that single road. Okay, so that is the concept of multiplexing. So you carry multiple signals on a single medium, or that, or from the perspective of that road versus car analogy, you can drive multiple cars on that road. So in that way you can efficiently use the capacity of the transmission medium. If you are driving one car on a very broad highway, then it's a wastage of the resources. Similarly, in a communication channel also, the channel capacity of the transmission medium is high, and if you are sending one signal through it, then it's a wastage of resources. So a common practice is to have multiple signals like this. So you have n signals all multiplexed together, and through this single link you are sending n signals in n parallel channels, and then at the receiver you are demultiplexing to get back your n outputs again. Okay, so in that way your cost per kilobits per second of transmission declines, and you can have an effective increase in the total data rate. Okay, so there are two types of multiplexing techniques. One is the frequency division multiplexing, and the other one is time division multiplexing. Actually, there could be more than these two types of multiplexing techniques. You will learn when we will be discussing 3G, that you can also have code division multiplexing. So, and even in frequency division multiplexing, you have different types there as well. In optical communication, we use wavelength division multiplexing, which is again a type of frequency division multiplexing, but we call it wavelength division multiplexing. You can have orthogonal frequency division multiplexing also. So main broad categories are these two, and then there are many other multiplexing techniques as well. So the basic idea in frequency division multiplexing is that you are taking advantage of the fact that the useful bandwidth of the medium exceeds the required bandwidth of a signal. So you can have different channels at different frequencies, and you can you can send them together on the actual transmission media, which has the total bandwidth given by the sum of the individual channel bandwidths. Okay. And in case of time division multiplexing, you are taking advantage of the fact that the achievable bit rate of the medium exceeds the required data rate of a digital signal. So now, in case of TDM, you are working with the time aspect. So here, different channel have different data rates, okay, and you are combining them together so that the total data rate of all these channels can be supported by the capacity of the channel. Okay, so with this I will stop here, and then we will resume again in the next video lecture. Thank you.